Hey Fizz Kids, and today we're going to talk about kinematics in two dimensions. And the specific kinematics in two dimensions that we're going to be studying for the purpose of this class is actually called projectile motion. So let's get started. What is projectile motion? So projectile motion is just when the motion of an object is basically the motion that an object experiences whenever it's launched into the air and it's subjected to gravity. So like we could kick this football and it travels this way. We would call that projectile motion. It's really the only thing that's acting upon it is gravity, and it's similar to free fall, but think about it as a free fall in two dimensions. So rather than just going straight up and coming back down, we're actually moving up and down in the y direction, and we're moving left and right in the x direction. But here are sort of the principles of projectile motion. So the path that our object follows basically is a parabola. So as we kind of go from start to top, if we look at this path here, the actual trajectory of our ball or object is going to be a parabola. And that the velocity is always going to be tangent to that parabola. So we're always, like in this case, right whenever we launch, our velocity is pointing straight out. And then as we go down further and further and further, our velocity is just a tangent to there. And if we wanted to, as we learned yesterday, because velocity is a vector, we can break that up into an x and a y component. So like here at first, we only have an x component, we have another x, an x, and we can also break it up into y components. And this will actually help us analyze the motion better. Because it is a vector, we can actually analyze that motion in the x and the y direction independently. So like the motion of the x doesn't really matter what the motion of the y is. The only thing that's connected is actually the time. So the time in the x and the time in the y direction is the same, but the velocities and the distances are often going to be different. So basically, so whenever we move in the horizontal and x direction, because we're not going to really worry about friction or air resistance or anything like that, that means our acceleration in the x direction is 0, which means we have a constant velocity. So our x velocity that we start with is going to be the exact same x velocity that we end with, and it's going to be constant the whole time. So it doesn't matter if we're at 0 seconds, 1 second, 2 seconds, 3 seconds, 4 seconds, as long as we haven't hit the ground yet, we're going to have the exact same x velocity because there's no acceleration. In the y direction, however, the velocity changes because our acceleration is going to be that acceleration due to gravity. So if you notice here in our example, we start off with no y velocity, but then as we get further down and time goes on, our y velocity increases at that constant rate because of gravity. One thing to sort of remember here is that while the x component doesn't change, and the y component does change, the overall velocity is always changing. Not only is the velocity going to be increasing, but it's also going to be changing its direction. So like the overall velocity vector, as we learned yesterday, that velocity is going to be equal to like the square root of our x velocity squared plus our y velocity squared. And we can do that inverse tangent of y over x to give us our angle. This value here is always going to be changing because even though Vx squared is staying the same, Vy is constantly changing. And that's what I just talked about. The resultant velocity is just that vector sum, or that square root of Vx squared plus Vy squared. It's going to give us that overall velocity. So what does the motion of an object that's thrown upward look like? Well, even though we're not being launched at the table like in the problem before, because there's no acceleration in the x direction, our velocity in the x direction is going to stay the same. So like Vx here is the same as Vx here, which is the same as Vx here, which is the same as Vx here, and it's the same as Vx here. It's a constant velocity the entire time. The y velocity, however, is going to be changing. So pretty much from here to here until it reaches that maximum point, our velocity in the y direction is decreasing. And then from here to here, our Vy is going to be increasing, but in the negative direction. At the very, very top of our point, at our maximum trajectory, and remember this with free fall, whenever we get to that maximum point, our velocity is 0. Well, whenever we talk about projectile motion, whenever we're at that maximum height, our y velocity is 0, but it still has an x velocity. So if you wanted to find the actual resultant velocity or the actual velocity, it would not be 0, but the y velocity at the very top is going to be 0. And then we can actually use that to find out what the maximum height is, or a whole lot of other things about our problem. Our velocity in the y direction on the same side at the same height is actually going to be the same magnitude, but opposite direction. So like we can really see that well right here. The magnitude of velocity at this point is the same as the magnitude at this point. Like let's say we could call that 1 meter per second and 1 meter per second. The only difference is this is positive 1 meter per second, and that is negative 1 meter per second. So because it has that parabola shape, those velocities are going to be symmetric on each side. But remember, that's only true for the y velocity. The x velocity is going to be the exact same magnitude and direction at every point in our trajectory. And finally, I know you probably thought they were done, but they're not. The equations to kinematics can be used to solve for projectile motion. What we have to remember with projectile motion, this is sort of the key thing, this is really the only tricky part, is that we have to make sure we separate everything into the x direction and everything into the y direction and analyze those two components separately. And typically, it's really going to be just that velocity that's given to you. And you might have like some velocity that's given at some angle to this. And the first thing you want to do is you always want to figure out what that x component of your velocity is and what the y component of your velocity is. It's knowing that is going to be able to allow us to sort of analyze the motion better. In that x direction, we have constant velocity. So once we figure out what that x velocity is, it is going to be the same the entire time. There's no acceleration in the x direction. We're saying, you know what, air resistance, for the purpose of this class, and really, it doesn't really play much of a difference, especially with small objects. Y velocity, or the y direction on the other hand, after you find that y velocity, it behaves very much as free fall does, because the only acceleration is the acceleration due to gravity. So as we're going up, we're going to be slowing down, 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 and then we'll reach that maximum height where we have 0 velocity, and then we start going down, 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 and we're going to speed up in the negative direction. But at every point in the curve, even when we're at 0 velocity in the y direction, the acceleration is still negative 9.8 meters per second squared. Make sure you remember that even though we do have at that one point at that maximum height, there is a 0 velocity, we still have the same constant acceleration in the y direction. But finally, kinematic equations for projectile motion. They are actually the exact same equations. We don't have to memorize new equations. We don't need to know anything new. We can use the exact same equations to study this motion. However, what we have to do is we have to break it up into x and the y direction. And basically, with the way that the x direction works, that horizontal direction, we know that our acceleration is 0, which means my final velocity is always going to be equal to my initial velocity. We can actually derive that from this equation here. So if we plug in 0 for a, we just get vx is equal to vo. And then finally, whenever we use our displacement equation here, we know that our final position is equal to our initial position plus our initial velocity times our change in time. Pretty cool. And I mean, I don't have it worked out here, but if you did simplify this equation, we have that vf squared is equal to vo squared plus 2a times x minus xo. Well, we know that a is 0, so this would just be vf squared equals vo squared, or vf is equal to vo. So it doesn't tell us anything new. And always make sure you put like little subscripts x after everything. That way you know we're talking about the x direction. So that's how we can simplify the horizontal direction for projectile motion. Our position versus time graph for projectile motion, just looking at that x motion, because we can split them up, is going to be a nice linear line. And our velocity versus time graph will be a horizontal line because we have constant 0 acceleration. In the vertical direction, we know that our acceleration is going to be g. It's going to be negative 9.8 meters per second squared. So we can actually kind of take our three kinematic equations, we can plug it in, and we find that our final velocity is equal to our initial velocity plus g times delta t. Our final position is equal to that initial position plus v0y times c plus 1/2 and get g t squared. And then finally we can plug into our very last equation here. Notice once again we are making sure to put those little subscript y so that we know we're talking about the y direction. Once again, I'm going to stress this again and again and again. I'll say it all the time because people always forget it. But whenever we analyze the motion for projectile motion, we must split it up into the x components and the y components and analyze them differently. The only thing they have in common is that the time is the same. So this delta t is the exact same as these delta t's. But other than that, they're not different. They're going to be very different motions. So your x is separate from your y. The only thing that connects them is that time because they happen in the same time span. If we look at our y direction or that y motion, our position versus time graph is going to be a parabola. Our velocity versus time graph is going to be a negatively sloped line, and then our acceleration versus time graph will just be a horizontal line at that negative 9.8 meters per second squared. That's what the acceleration due to gravity is. Launch angles. So with projectile motion, we can launch it at different angles, and depending on what the angle is, we can actually we get different components of our velocity. So like if we all launch at the same overall velocity, depending on the angle, sometimes our y component might have more velocity, sometimes the x component might have more velocity, sometimes they might be the same. And this all has to deal with, and it basically can tell us how far something goes. So based upon the angle that something's launched, we can tell what's going to have maximum height and what's going to have maximum range. And in this case, launching at a 90-degree angle will give you a maximum height. So if you want maximum height, you want to launch that thing straight up. And that's because if we launch it straight up, all of our initial velocity kind of gets transferred in the y direction, which means it's going to take longer for us to slow down, which means we can get to a higher height. However, if we want maximum range, so we want to go as far, we want to shoot as far away as possible, we actually want to do it at a 45-degree angle. That's going to give us the maximum range. So 45-degree angle is range. That gives us the furthest range for a given launch velocity, and the maximum height is based off of shooting it just straight up to that 90-degree angle. And if you wanted to, you could actually, there's a really beautiful derivation for how you can find out what this maximum range is by combining the two, the x and the y motion. You solve one of them for time and you plug it back into the other equation. And I would definitely, if you want to and you're interested in that, definitely go out and do that if you would like. But by no means do you have to, or you don't like math that much, don't feel like you're obligated to sort of see and derive how you get this maximum range. So we have a problem, and I want to do this one example problem before I end this video. So we have a motorcycle that speeds horizontally off a 50-meter high cliff. At what speed must the motorcycle leave the cliff if it lands on the ground 90 meters from the base of the cliff? Well, the first thing that we have to do is we'll always draw your picture, but the picture is provided for us. But we want to list our knowns and unknowns. So in this case, in the x direction, we want to know what that velocity is. What x velocity or what velocity do we have to drive off this cliff in to make it 50 meters? And we know that it's all in the x direction because we're driving straight off the cliff. So all of our initial velocity will be solely in the x direction. We know our acceleration in the x direction is 0. We know our initial position is 0 meters because we're going to call this 0 right here, and our final position is 90 meters, and we don't know what the time is. In the y direction, okay, well, because all of our initial velocity is in the x direction, that means our y initial velocity must be 0. We know that our acceleration due to gravity is going to be negative 9.8 meters per second squared. And we know that our initial position is 0, because I'm going to call this 0 up here. And our final position is going to be negative 50 meters, because I go down 50 meters. And once again, I don't know what that time is. So I want to find what this final y, what the x velocity is. So if I kind of look here, I can look at my equations and I see, okay, I know that xf is equal to the xo plus v0t plus 1/2 at squared. My a is 0, so I know that this is going to be xf equal to v0t. And look, okay, well, I know that vx is equal to v0x. So in this case, I look at this and I say, well, I want to solve for this. So I want to find that v0x is going to be equal to my xf over t, but I don't know what my time is. How can I find time? Well, I'm not going to say all the time, but 90% of the time, you're going to be able to find time using the y direction. So in this case, if we look at our y direction, we know that our final y position is equal to that initial y position plus our initial y velocity times time plus 1/2 our acceleration in the y direction times time squared. So if I look at this and I can start, I want to know what time is. Well, I'm going to simplify it a little bit. My initial y position is 0, so I would just have yf is equal to, so that's going to go to 0. v0y is also 0, so I can get rid of that. And I just know that yf is equal to 1/2 ay times t squared. I can solve this for t, and I would get t squared is equal to 2yf all over ay, or t is going to be equal to the square root of 2yf all over ay. I can plug directly into here and I can actually figure out what my time is. So in this case, my time is going to be equal to that square root of 2 times negative 50, all divided by negative 9.8. And I find that the time that it takes for my motorcycle here, let me grab my calculator, to hit the ground is actually right around 3.2 seconds. So then what I would do is say, okay, now I have my time. I look back over here at this equation. I know what my final position is, and now I know what my time is. So I can go ahead and plug that in, and I find out that my initial velocity in the x direction, or my initial velocity, is going to be equal to xf, or in this case, that 90 meters, all divided by 3.2 seconds, which would give me right around 28.13 meters per second as that initial velocity that is necessary to sort of launch off the cliff. So that is all I have for you. I want you to go and answer the video check, which you can find below this video in Canvas, and I will see you all in class where we can talk more about projectile motion.